Grejtak, and my research is on improving the combustion chamber with thermodynamics and computational fluid dynamics, another step for emission reduction. So first of all, let me tell you a few words about the background of my research. Last summer I did an internship back home in Slovakia for this one company, Computer Control Technology, or CCT. This company does automatization, control, service for industrial companies, and we were working on a blast furnace for production of magnesite clinker. So this is the original model of the blast furnace we were working on. So let me describe it to you for a second. So here's an opening, and the material was coming here. The material was magnesite rocks, and the material was burned and decomposed here. This is the cross section. You can see we have 6 burners all around, and here we got the product. The product was the dust, and later on they made bricks of this dust. However, this blast furnace had combustion issues. Sometimes it happened that the material wasn't properly decomposed. Instead of the dust, we got magnesite rocks, so it means that the material just went through the blast furnace. Then when we increased the temperature inside by increasing the gas flow, the material was completely burned, so we couldn't use it, and also there was a high amount of methane in the combustion chamber and high amount of CO2 in the air. So we figured out that the problem is most likely going to be in the gas burner. So one of the problems could have been the design, the improper ratio of gas and air, or ineffective mixture of gas and air. So I was thinking that this can be a good research topic for the UGROW, so I decided I'll work on it. So we decided to solve this problem with computational fluid dynamics. We couldn't solve this problem with analytical solutions because analytical solution cannot predict the behavior of gas and air in the mixture of gas and air inside a gas burner, or the thermal processes inside of the blast furnace. Actually, many years ago, Dr. Wang, my mentor, did research on turbulent mixing of gas and air in a gas burner. He compared a few different models. For example, this is the model that is used right now, this blast furnace we are working on. And this is a new model. The difference is that in here we have inlets on the side and one over here at the beginning. But in this model is called concentric, and we have gas inlet and inlet situated on the same side. So it means they're all coming the same way from the same spot. And in his research he proved that this concentric model gives us the best mixture of air and gas. So I was still in touch with this company while I was doing this research, and I told them about this idea, and they said, okay, it looks good, so we should work on it. So before we started modeling or making any simulation, we had to study the properties of gas and air. So this is a combustion equation. We can see that the methane reacts with oxygen and gives us CO2 and 2 moles of H2O and also heat. We calculated this heat, and it was 800.74 kilojoules per mole. We can see that there's a negative sign. It means that the energy was released, the heat was released, so this equation is exothermic. Then we calculated the equilibrium constant, K, and it turned out to be big number, which means that the reaction is only one way, so the reverse reaction. Then we calculated the molecular weight of methane and oxygen. Air consists of 80% of nitrogen and 20% of oxygen. So when we did the balancing ratio of methane, we had to also add methane plus air, but we have to consider 10 moles for air because it consists of 2 molecules of oxygen and 8 molecules of nitrogen, and we calculated this balancing ratio to be 5.2%. These are the input parameters that the company gave me, both for gas and air. They gave me the flow, pressure, and temperature, and then we used these parameters to calculate mass flow ratio for both gas and air. So first for gas, we had to calculate velocity. We got 280 normal meters per second. When I said normal means that it was measured at the temperature of 273 kelvins and pressure of 101 kilopascal. Now we have to convert these normal meters to seconds to actual meters per second by using ideal gas law. And we can see that the velocity is 85 meters per second. So we can see that the difference is really big, and it's because the pressure of the gas was 250 kilopascal, which is a lot in comparison with normal pressure, which is 101 kilopascal. Then we did the same for air. As you can see, the normal velocity and actual velocity are pretty much the same because the pressure for air was only 6 kilopascal, which is a very small number. Then we also calculated the balancing ratio between mass flows of air and methane. We also, the balancing ratio was actually methane over air plus gas. So we can see that now the ratio is 5.34, which is not the same as 5.2. Actually, these two results has to match. So one of the problems that the company had, most likely, is that they were using too much of gas. So one of the suggestions is that they're gonna have to reduce the gas flow. Maybe that's why they had so much methane in the combustion chamber. Then we have to consider Navier-Stokes equations. Navier-Stokes equations are one of the most important equations when we deal with computational fluid dynamics. Why? Because they study the motion of fluid and they can predict the velocity and geometry for velocity and pressure for different geometries. Also, we had to set the boundary conditions. It's also very important. So for the inlet, we already calculated velocity, pressure, and mass flow. And for the wall, we have to consider non-slip conditions. So what does it mean? Non-slip means when fluid touches the wall, it sticks to the wall because the velocity of fluid, the moment when it touches the wall, is 0, and also the velocity of the wall is 0 because it's a stationary wall. So these both velocities equal, so that's why it's a non-slip, it sticks. Then we consider roughness, radiation, convection, conduction, heat transfer, heat flux, and radiation. And we define outlet as a pressure outlet as a 0 pascals. We considered the K epsilon turbulence model because this model simulates the characteristic of a turbulence flow. So these are the results we got. We used softwares Adina and ANSYS. For Adina we did 2D model and 3D model. So we can see these are the boundary conditions. So we define the wall, and we define the gas inlet and air inlet, also for the 3D. It's also one of the 3D models. The burner, with the air inlets here and the gas inlet here. From the results we got, temperature can also tell us a lot about the quality of mixing of air and gas. So we can see as we go on. It's very important that the mixture is really good here, because here's a lighter and flame comes out of this spot. And we can see that the temperature is getting more and more uniform towards the end. This is the velocity magnitude. We use 2 different softwares. You can see that pretty much look the same. We have a turbulent mixing here, also turbulent. Turbulent is important because we need turbulence to mix gas and air. We can't consider laminar flow, of course. And here are the species for methane, only the methane. You can see whether we set the boundary conditions really good. You can see it's just methane, and now here comes the mixture, because the air comes from here, air comes from here. So we can see that it's mixing here, and we don't have any leftover methane here. Also for the oxygen, we also set the boundary conditions really good. We have just oxygen here, and we can see as soon as it gets in contact with methane, it mixes pretty well. We don't really have any leftover oxygen here. My goal was to finish the whole research by the end of June, and unfortunately I realized that computational fluid dynamics is extremely difficult and very demanding, and it really took us a long time just to set the boundary conditions. If you set just one boundary condition correctly, the whole simulation is wrong. So many times we had to start over and over and really dig into it and figure it out where was the problem. So these are the results we got so far, and I want to continue with this research this summer, and I want to simulate the flame is coming out of the gas burner, and also I want to simulate the thermal processes inside of the furnace, blast furnace, to see the convection, conduction, radiation, and how well is the material decomposed inside. I would like to thank McCoy School of Engineering for the support, and Dr. Shaw from Chemistry Department for helping us with the heat generation and balancing equation. And I would like to thank the company Computer Control Technology for providing all the data.